Hello guys, welcome back. Let's go deeper into IPv6 addressing in this particular video. My focus over here is going to be IPv6 address types. Although we don't have classes in IPv6, we do have different types of IPv6 addresses. So in this particular video, we're going to be taking a look at what are the different IPv6 address types, basically global, unique local, link local, and multicast addresses. These are the four different address types. Why do we have it? What are the usages of each one of them? We will be taking a look at in this particular video. So with that in mind, let's get started. As I said, in IPv6, we do not have a class system. So we don't have a class A address or a class B address or a class C address. We have a fixed system in terms of the network bits and the host bits. The network bits basically are the first 64 bits, or you can say the first 16 hex digits, or if you want to take a look at it from the block perspective, first 4 blocks, because each block is a set of 4 hex digits, and another 64 bits for what? The host portion, which again is another 16 hex digits, making the total of the 32 hex digits, and another 4 blocks, which is total of 8 blocks. So that's what these two are talking about over here. The default mask is /64, which we have discussed. This should be a recap. Now, although we don't have a class system, we do have different types of addresses which are used for different things. Some of them we do have an example of in IPv4, but one of them is unique, which is new for IPv6 addresses. What are the different types of addresses and how do they correlate with the IPv4 addresses? Pardon my drawing skills. So the global unicast address in IPv4 is your public address. What we call the public address, the address that is routable on the internet, in IPv6 is called the global unicast address. This is the one that the ISP is going to assign. The other one is a unique local address. This is equivalent to your private address space. All right, this is locally significant, local on the network. To your company. So basically, if you want to do testing of IPv6 addresses, you can use these unique local addresses, ULAs. Now, I'll skip the link local for right now. I will go to the multicast so that we have some type of comparison. Multicast is just like your multicast address in IPv4. It's your group address. If you want to send a specific type of traffic to a group of devices, I would send it as a multicast address. Similarly, in IPv6, I have a multicast address. This one you don't have an equivalent of in IPv4, so I'll give you a detailed explanation on the link local address. But these three, the global unique address is your public address, publicly routable address. Unique local address is like your private addresses, the 10, the 172.16 series, the 192.168 series that we discussed in the IPv4 video. And then the multicast address, which was the 224 range, 224 to 239 range. This is your class D. If you guys remember from IPv4, this is your class D address space, which we have an equivalent of in IPv6. It's a multicast address. The addressing numbers are going to be different, but the functionality is the same. So with that in mind, these are the 4 different address types. Let's go into and discuss each one of them, how they are formed, how do I identify a particular address as an IPv6 global address or a unique local address or a link local address or a multicast address. As I said, link local we'll discuss in detail because that's an address that you don't have an equivalent of in IPv4. Starting off, global unique addresses. As I said, these are your public address. These addresses are assigned to you by your ISP. So the ISP is the one that you will have that will have access to all these public addresses, and they're the ones that will be giving you public addresses. Okay, so these addresses are equivalent to the public addresses in the IPv4 address space, which is fine. Now, how do I identify a global address? Let's take a look at that. Let me go to my magical whiteboard, explain that to you guys, and come back to the slide. Now, for a global address, it is identified by looking at the first 3 bits. Just like in IPv4, we discussed that a class A address is identified by the first bit being 0, class B address identified as the first 2 bits being 1, 0. If you guys go back to that video, you can follow that, and the class C address is the first 3 bits being 0. Same type of thing is applied for a global address. The global address rule is the first 3 bits are, in terms of a global unicast address, is a 0, 0, 1. That's the rule. Now, if you take a look at a deeper look at the rule, the first 3 bits, now first 3 bits, I don't write an IPv6 address in binary, I write it in hex. And if you guys remember, 1 hex digit equates to 4 bits. So if that's the case, my first hex digit, which is equivalent to 4 bits, the first 3 bits of a global unique address are always going to be 0, 0, 1. So if I take a look at the first hex digit, so if I have a number like x, 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 colon, so on and so forth, the digit in question is just this digit, because this digit is equivalent to what? 4 bits, and I'm saying the first 3 bits are 0, 0, 1. So let's expand this bit over here. So what I'm saying is, in the first hex digit, the first 3 bits are 0, 0, 1, and the 4th bit in that, because it's 4 bits, is a variable. That means it can either be a 0 or a 1, because it's a single bit. Single bit gives you 2 combinations, 0 or a 1. So that basically equates to the the first hex digits has 2 combinations that makes it a hex digit. Or sorry, the first hex digit has 2 combinations that makes it a global address. One is 0010, 0010, or 0011. Those are the 2 combinations. So first hex digit is your indicator whether it's a global address or not. If the first hex digit is either a 0010, which if I do the conversion, 0010, which is 8, 4, 2, 1. So the only one that's on is 2. So 2, 2, 1, which is 3. So if the first hex digit is either a 2 or a 3, I know it's a global address. So the rule for a global address is the first hex digit is either a 2 or a 3. So when I look at this address, if I see a 2 or a 3, it is a global address. Understood? The bottom line, I wanted you guys to see why. This is the rule. This is the implication of the rule. End result, the first hex digit. Of a global unique address or unicast address is what? Either a 2 or a 3. So as soon as I see that, I know it's a global unicast address. So let's go back and take a look at the rules on the slide now and see if we have covered them. The rule for being a global address in IPv6 is that the first 3 bits are 001. That translates to the first 3 bits in the first hex digits being 001. By having the first 3 bits of the first hex digit to 001, you leave the 4th bit of the first hex digit to a variable. And that's what I was trying to explain to you guys. 001, this is the first hex digit. So this is a 2 or a 3. That becomes 0010 or 0011 because it is a variable on the 4th bit. So this is a 2 or this is a 3. To identify a global unique address, you need to look for a 2 or a 3 as a first digit. If the first hex digit is a 2 or a 3, any IPv6 address will be a global unicast address. And that's an example of that. As simple as that, don't complicate it. You know that if it's a 2 or a 3, it's a global unique address or unicast address. All right. Now, what about the private addresses? So this is your public address. You guys remember? Global unicast address in terms of IPv4 would be compared to a public address. So how about a private address? A private address is also available to you in IPv6. Now, what are the rules for a private address, which is not called a private address in IPv6? It's called a unique local address. Okay? The rule is the first 7 bits. So if it's first 7 bits, that means it is taking 2 hex digits into consideration. First 7 bits means 1, 2, 3, 4. That's 1 hex. 1, 2, 3, the second hex. So this is going to be my variable bit over here. R, the first 4 over here are 1, 1, 1, 1, which equates to an F. In the third one, it is 1, 1, 0. This is the fixed portion, leaving the 4th portion as variable. So if you write that, 1, 1, 1, 1, all ones is an F. 1, 1, 0, this is a variable, so it could either be a 0 or a 1. So the two combinations on the second hex digit are 1100, which is a 12. 12 equates to a C, or 1101, which is 13, which equates to a D. So the first 2 hex digits of a unique local address, which are your private addresses, equivalent to your 192.168 address space, 172.16 address space, the 172.16 what do you call it, 16 through 31 address space, and then you have the 10 address space. Those are your private addresses in IPv4. Here we don't have classes, it's a generic one. The private addresses, to identify them, is the first 2 hex digits FC, XX, or FD, XX. Now the reason I wrote the XX over here, if I start my private address as FC colon, that blows the rule away, because that FC colon means what? My first 7 or my first 8 bits are all zeros. That's wrong. So it has to be some 2 digits over here to make it a first 7 bits being FC. All right. So don't forget, don't write FC colon. It has to be FC. For example, what I generally do is I would write FC00 or FD00 to represent my unique local addresses over here. Now let's go ahead and analyze a slide and the verbiage that goes along with it. That is your unique local address. As I said, they are your equivalent to your private addresses in IPv6. The rule of the unique local address in IPv6 is the first 7 bits are what? 1111, 10. That gives you a combination of F, and this guy can be either a C or a D. So by having the first 7 bits as 7 bits is basically involving the 2 hex digits. You leave the 4th bit of the second hex digit as a variable. That means F, and 1100 or 1101, which is FC or FD in the first 2 hex digits. So to identify a unique local address, you need to look at for an FCFD as the first 2 hex digits. And I made sure you put the XX in the middle don't put this. This is a wrong or an invalid address. So this would be an invalid address because that would be 00F0, which is wrong. Has to be FC followed by any 2 digits. As I told you, what I generally do is I say FC00, which is good enough. These are my private addresses over here. So we've covered the two equivalents of the public and private addresses in IPv6. All right. The next thing that I'm going to take a look at is an address that is something that we don't use in IPv6. It's called a link local address. All right. What is this address? This is a system address. First thing that you need to understand, the link local address is a system address. It is automatically assigned by the system, by the device. Not only is it automatically assigned to itself, it is only used by the system. An end user generally does not use the system address by himself. He will use the unique local address or the global address. This system address is used for system services on the local segment. It is a non-routable address with a TTL value of 1. So I will not be able to communicate using this link local address with a device on another subnet. It's a non-routable address. So that's why I meant you don't have an equivalent of that. This is an actual non-routable address. Whereas when you have private addresses, which are called non-routable in IPv4, they're non-routable on the internet because of a policy, but in itself, it's a routable address. This address actually cannot be routed. So what is it used for? Let me write that down for you guys, or show you, demonstrate that to you guys. So let's say I had 2 devices that want to talk to each other for any type of system services on the local segment, be it a router, be it a PC, internal system services like ICMP. They want to find out the MAC address of the other device. They want to do a neighbor discovery, or the routers want to talk to each other for a routing protocol. When they communicate to each other for system services, like I just explained to you guys, they are not going to use the address that you assign to the interface. They are going to use this address called the link local address for communication for services that are not done by the end user. The end user traffic generated by you as an end user, is referred to as data plane traffic. Traffic generated by the system to set the network up or communicate for the purpose of system is called control traffic. So this might be your system generated traffic. The device itself is generating the traffic for its own self. This is called control plane traffic. So in other words, the control plane traffic that you're using on the same segment, on this particular segment, between devices on the same network, not going outside. If this router wants to communicate to another router on another segment for some, let's say a routing protocol like BGP, I'm not going to use the link local address for that. Link local, it's local only on the system, used by system services for control plane traffic. That's the purpose of the link local address. So you as an end user are not going to use it. The system is going to use it in the background. That's the first thing that you need to understand about it. Okay. Now that you understand the use of it, let's recap that over here. This is automatically generated an assigned address automatically. It is a system IPv6 address that is assigned to every IPv6 interface in addition to the address that is assigned. So if you assign your unique local or global unicast address, you will have this address assigned to you automatically. So every interface in IPv6 will have your normal unique local address or global address. Plus, the same interface will also have its own link local address, which it automatically generates assigned to it. Okay, the link local address is used by system services like routing protocols, ICMP for finding the MAC to IP bindings. That's how IPv6 does it based on the ICMP v6 protocol. That's what it's used for. So that's what I explained to you guys is the use of the link local address. Now that we have that in mind, now let's take a look at how does the system assign this link local address? How do I know it's a link local address? Just like the other address types that I have, a link local address also has its own rules. The rules for the link local address is the first 10 bits are, so again, if it's 10 bits, it's 4 bits on the first hex digit, 4 bits on the second hex digit. In the third hex digit, you have 1, 2, 3, 4 bits, the 2 bits over here. So the entire first, entire second, plus 2 bits on the third. So the rule for that is the first 10 bits are 1, 1, 1, 1, which makes the first hex digit as an F, 1, 1, 1, 0, which is 8 plus 4, which is 12 plus 2 is 14. 14 in hex is E. And this is where that information that I gave you guys about the binary to hex conversion plays a big part. And the last 2 bits out of the 10 are 1, 0. This is fixed. So now over here, my variable bits are 2. If I have 2 variable bits, that means I have 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. So that makes it FE 1000, which is 8, or 1001, which is 9, 1010, which is 10, but you don't write 10. 10 is A, and 1011, which is B, which is 11. Okay, now if I look at my IPv6 address, that additional address that the system assigns, how do I know it's a link local address? It's either going to have an FE8X in the first 4, FE9X, FEAX, X meaning any digit like 0 or whatever, and FEBX. So for example, I would say FE80, FE90, FEA0, or FEB0. So this is what generally you're going to see as a link local address. So again, let's take a look at the slide, see if this is what we're getting. The link local address is automatically used. We've done that. The rule for being a link local address in IPv6 is the first 10 bits are 1111, 1110, which is E, 10 in the third hex digit. By having the first 10 bits of the first 3 hex digits, again, as 1111, 1110, you leave the third and the fourth bit of the third hex digit as variable, which is represented over here, which is an F, E, and this is where the variable comes in, which is 8, 9, A, or B. So that's what you're going to see as a link local address, and I've represented that over here for you guys. So this leads to the combination of 1111, 1110, 1000, which is FE8, 1111, 1110, 1001, which is FE9, same thing, 1010, which is A, 1011, which is B. So the example again for a link local address, which you guys don't use as much, but is extremely important for the system to use in the background, is either FE8, FE9, FEA, and FEB. It automatically assigns it. All right. Now this is a full address, right? This is going to be used by these devices to communicate to each other. So it needs the host portion as well. This is just one portion of it. What about the host portion? It uses a special mechanism, and which we'll go into detail about later on, but I'll explain that over here anyways. It uses a system where it incorporates the MAC address as part of the host portion. So what it does is, because it needs a complete 128 address, FE8 is just part of the network, or FE9 or FEA or FEB. Let's take FE8 as an example. So the address, the way it assigns it, FE80, colon colon, that means a set of contiguous zeros. Now what it does, it takes the MAC address. The MAC address, which is your NIC address, is basically a 48-bit address. Again, represented in hex. If you break 48 bits into hex, it becomes a 12 hex digit number. Now what they want to do is they want to use this 12-bit hex digit number as part of its host portion. So they use this as to represent the network portion. And now I need to come up with the host portion. But I'm missing something. I'm missing 4 hex digits. Why? The total number of host portion is 16 hex. The MAC address is only 12 hex. And now, just to make sure you guys understand that, the MAC address itself, the 6 hex digits that you have 2 identifiers. It's a unique identifier for each organization. So the first 6 hex digits are assigned by this committee called the IEEE to a vendor, saying, hey, listen, go ahead and manufacture your network interface cards or layer 2 addresses based on this 6 hex digit number. This is a number that is administered by IEEE to make it unique universally. And then the individual vendor will go ahead and manufacture different NICs and assign unique addresses to the device by using another 6 hex digits. So this is something that the IEEE assigns to the vendor. Let's say you have a vendor called 3Com that manufactures NICs. Cisco manufactures NICs. So you'll assign this to Cisco. Cisco then in turn will assign individual NICs 6 hex digits to give unique addresses. Now, what they do in the IPv6 address, why am I getting into the MAC address part of things? Now, what they do in the IPv6 address, they use a unique identifier for the company, which is the first 6 hex digits of the network interface card as the first 6 hex digits over here. So hex, 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 that's 4, hex, and hex. This is the 6 hex digits that is assigned to the vendor ID. Then it puts a fixed number in the middle. This is the number that you will always see in this auto-assigned link local address, FF, FE. That's the filler. If you guys remember, the total number of host portion hex digits that I needed was 16. The MAC address was only giving me 12, out of which 6 I've used up over here. I'm missing 4, and this is the missing 4. So this is your filler in the middle of the host portion. Now I'm left with another 6 to fill up, and that comes in from the other 6 addresses, 6 hex digits that are assigned by the vendor to the individual NIC. So that would be another hex, colon, HH. That becomes the full IPv6 link local address, which is derived from the from the MAC address by putting in a filler of the 4 hex digits FFFE in the middle. Now, there's one more rule that is there for future enhancements. If you go and take a look at the RFC for this auto assignment, it basically says that in order for future enhancement where the programmers, the application developers could distinguish between addresses that are virtual versus addresses that are manufactured or assigned by the IEEE universally assigned, there's a bit in the first 8 bits that is turned or inversed to make sure that this address that you have assigned or that has been auto-assigned is identified. At this point, I'm not really doing anything with it, but IEEE plans on giving that as an ability to classify traffic in the future. So I'm just going to tell you how it works, but in terms of today, there's no use for it. So what is that rule? The rule is in this, let's say my address was 000001, and then I would have an FF sorry, I would have these two FFs over here, colon FE, and then I would have my MAC address that was assigned to me by my vendor. So let's say that address over here happens to be 71AB01 as an example. That's the MAC address. So the MAC address would have been 0000 colon 0171 colon AB01. In this address, this portion is the vendor code. This is the unique address that the vendor assigns to that NIC. So what I've done over here is taken 0001 FFFE 71 AB01 and split it like that. Now, what happens is the rule for that unique universal local bit is the 7th bit over here, which is inversed to identify it. Hey, listen, this is not an address from the a normal MAC address. It's basically administered local or it's locally significant, is inversing that bit. What do I mean by inversing that bit? If you take a look at the first two hex digits in binary, the first hex digit is 0000, that is untouched, so it'll be 0. The second hex digit that you have over here, it starts off at 0001. Now, if you take a look at what is the 7th bit over here, 1, 2, 3, 4, 5, 6, 7. So this is the bit in question. This gets inversed. If it's a 0, it becomes a 1. An indication that this is something that has been manufactured locally. So 0000, 0010 is what it becomes. So this second digit changes to what? The MAC address over here, the host address over here becomes 01, which is 1 becomes a 2. 1, 2, 4, 8. Remember, this is in binary. I need to write it in hex. So it becomes 02, 00, 01, FF, colon FE, and then the remaining of the MAC address, which is AB01. So this is what the address is going to be. So if I had to write this address in its totality, after it has been reassigned automatically to the link local address, again, I'm just showing you because this also helps us later on when we do auto assignment of addresses. So this address, a link local address which is auto assigned, will look like this. Based on the MAC address of what? The MAC address, I'm assuming the MAC address is 00000171 AB01. This is the 12 hex digit MAC address, and I want it to be incorporated as my host address. So this becomes 02 00 colon 01, and then the filler FF FE, and then the remaining of it 71 colon AB01. This is your host portion. So every address, every device will be assigned an address based on this format. Now, what if, just to make sure you understand this properly, again, this is not just putting a 2 over here, it's inversing the bit. Let's say, hypothetically speaking, my address over here, my MAC address over here was 1234 0171 AB01. So if that's the case, how do I inverse it? Let's take a look at that. Again, I'm going to take the first 2 over here and expand it. 0001 is 0001 is 1, and 2 I would have written like that. Sorry, because this bit is the one that makes it into a 2. So in the first 2 hex digits, it's 0001, which is 4 bits, 001, the 7th bit 0. Now I inverse it. If I inverse it, it becomes 0001. Inverse it becomes, inverse means opposite of it, 00. So my MAC address over here would have been, based on this here, I put the same 71AB00, that's okay. 123401 would have become 1, still 1. 2 becomes a 0, it inverses it. 3, 4 are the same. 0, 1 is the same. So if you take a look at it, I have inversed the bit. So it's inversing the bit, it's not turning it on, it's just inversing it. That's something that you need to be aware of. So this address is automatically assigned. The reason I went into so much detail over here is it's going to help my lecture later on when I do the auto assignment of my normal unique local addresses or the global addresses, because in there I also have the ability to use a MAC address as part of my host address. All right, so this part is not on the slide, but it's good to understand how it assigns the MAC address as part of your IPv6 host address. So let's go back over here. We've done this rule, so no, not this one, sorry, this one. It is auto-assigned. It also needs to take the host portion into consideration. It uses the MAC address automatically as part of the host portion. We'll take a detailed look at the auto-assignment later on of the host portion. We have taken a look at it over here as well, but we'll do more examples of that later on in another video, because we do the auto-assignment of MAC addresses in this particular video series. I'll explain that at that time. So that's your link local address. Again, the main thing that I need you guys to understand, because this part is done automatically, so I'm not really too concerned about that. The main concern is understanding what is a link local address used for. It's a system address which is used by the device for its system services, not end user services. When I browse to the internet, that's an end user service. When I run a routing protocol for two routers to exchange routing information to each other, that's a system service. So when I use a system service, I'm going to use the link local address for communication. Okay, let's say FE80:::, whatever. That's what the link local address is. And that's why I said in IPv4 I don't have that, because those routing protocols will not use any, they don't have any link local address. They would assign or use the assigned address for these communications for system services. That's the difference between the two. All right, so last address, the multicast address. Again, multicast address is used for one-to-many communications, just like in IPv4. It's just the rule is different. In IPv4, a multicast address is given its own class, class D. And how do I identify a multicast address in IPv4? It's the first hex digit is between 224 to 239. The reason for that is the first 4 bits are 1110, which gives you that range. That's in IPv4. In IPv6, the rule for multicast address is very simple. The first 8 bits are 1111, 1111. It's fixed, so it's because it falls on your octet boundary, not your hex digit boundary. It's 2 hex digits. So anytime you see the first 2 as FF, it indicates it's a multicast address. So any address that starts with FF in the first 2 hex digits, again, not zeros, not FF colon, which is wrong because that means it's 00, right? So it has to be what? This guy over here, FF and 2 digits, and then whatever you want to use. Sorry, this is no, there's no mask over here. It's a copy and paste type of thing. So there's no mask on multicast addresses because there's no network or host portion for that. This is identified as a multicast address. Now, some common multicast addresses in IPv4, I had the same. The routing protocols use multicast addresses to communicate to another set of routers. So for RIP in IPv6, I used an address of 224, which is a address that is reserved for RIP in IPv4, 224.0.0.9. Similarly, in IPv6, the same type of address for RIP, the routing protocol, is FF02::9. That's the address that RIP-NG, which is the RIP for IPv6, uses to communicate. Now, I also told you that the routing protocols use the link local address. They do. The link local address is what my source address is going to be. So if I'm running any type of routing protocol, my source IPv6 address is going to be your link local address, whatever that is, FE80 and that MAC address. The destination is going to be FF02::9 for RIP. It's the destination. So in the destination, RIP would use this. Source, it would use the link local address that we discussed in the previous slide. So if I was not running RIP, I was running EIGRP. EIGRP would use FF02::A. The same type of thing in IPv4 would be 224.0.0.10 because EIGRP has this address assigned to it. OSPF uses two multicast addresses even in IPv4. Those addresses happen to be 224.0.0.5, 224.0.0.6. The similar type address in IPv6 is FF02::5, FF02::6. Everybody understand that? You guys are okay with this? Hopefully. So this is your multicast address. So to recap, how many type addresses address types do I have in IPv6? The global addresses, global unique addresses, which is like your public address. You have the unique local address, which is like your private address in IPv4. Then you have the multicast address, which is basically the same thing as your multicast address in IPv4. And the fourth type that does not exist in IPv4 called the link local address. This is that address that the system auto assigns itself for its system services. All right, so these are the four type of addresses that you have in IPv6. Hopefully that clears up some of the doubts that you have. Let's take a look at the review questions and then we'll jump on into the next video. Some review questions over here that might help you identify or recap this. Identify the type of the following IPv6 addresses. How do I know what type of address this is? Because I see either a 2 or a 3, I know it's a global address. You can call it global unique address, or sorry, global unicast address or a global address. FD, FC or FD are your unique local addresses. So this would be your unique local address, the private address. FE80, FE8 represents the link local address. What type of IPv6 address is non-routable? It actually does not route because anytime the link local address is assigned, it's going to have a TTL value, time to live value of 1. That means it will die on the first router. It won't be able to forward it. What type of IPv6 address is routable address but not on the internet? One that cannot be used on the internet is your private address, which is your unique local address. So within your network, you can route it, but you cannot route it globally. What type of IPv6 is globally unique, which is a global address? Global unicast address or global address. How do you identify a multicast address? The first 2 hex digits are FF and then whatever. That's a multicast address. Hope you guys enjoyed it. See you guys in the next video. Don't miss it. It's IPv6 subnetting.